Hello student, hi, good evening. So today we are going to discuss about group fifth, group fifth, group third and fifth semiconductor. Okay, so group third and fifth, group third and fifth semiconductor. So see here, group. So this is today's discussion is about group. So this is my group third, and group third and fifth semiconductor. Okay, so group third and fifth semiconductor. So group third and fifth semiconductor, as we have been discussing in the last lecture about what about donor and acceptor impurity. Yes, as we have seen and have been discussing about impurity, donor impurity and acceptor impurity atoms in what impurities in group fourth semiconductor element, group fourth semiconductor element that we have seen in the last class. Okay, so that is over what that is indirect band gap semiconductor material. Okay, so now here we are seeing that is over elemental semiconductor material, where we have seen that donor and acceptor impurities in silicon semiconductor. So today we are going to see the group third and fifth semiconductors. These are my compound semiconductor. Compound semiconductor. These are compound semiconductor. Okay. So now in compound semiconductor, what we will see here, the situation in this compound semiconductor, such as gallium arsenide. Situation in this compound semiconductor is complex. Yes, more complex. Yes, the situation here is more complex than in case of silicon semiconductor, elemental semiconductor. Okay, so what type of situation that we will face here? See here, gallium arsenide. Gallium arsenide is what? It's a third and fifth group element. Yes, third and fifth group element. It is like a hybrid. Yes, hybrid semiconductor or compound semiconductor. Now, if we see here, if group second element. Yes, if group second element like zinc, group second element, beryllium, zinc, beryllium. Okay, if group second element, these are element, group second element like zinc, beryllium and cadmium. What? Cadmium. Zinc, beryllium and cadmium. If these what element? These element will what? Will enter into what? Into this gallium arsenide. Yes, into this gallium arsenide as what? As substitutional. Okay, if this group second element will enter into what? Will enter into the group third and fifth gallium arsenide as a substitutional impurity. Okay, if they will add into substitutional impurity. Okay, substitutional impurity. So then, okay, so if this will come, okay, so this will enter. If they will enter in what? If they will enter into what? Into gallium arsenide. That is group third and fifth. Okay, if they will enter into this group third gallium arsenide, group third and fifth gallium arsenide as a substitution. Okay, as substitutional impurity. Substitutional impurity. Okay, So if this group second element like zinc, beryllium, cadmium enter into what gallium arsenide, that is compound semiconductor as substitutional impurity, and replace the group third element in this element. See here, this is like here germanium, here this is my gallium, and this is my arsenide. Yes, this is my arsenide. This is my gallium and this is my arsenide. If you see gallium outermost shell, how many? How many electron is there? 3. If you see arsenic outermost shell electron is how many? 5. 5 electron. So these are 3 electrons. These are 5 electrons. Means here octet is full. Means it is stable. It is stable. Gallium arsenide. Yes, 3 5 is equal to 8. 8 means octet is completed. So this is what this compound semiconductor is stable. Now what is happening? Now what if this group second element such as beryllium, zinc, cadmium will enter into what? Enter into compound semiconductor such as gallium arsenide. That is group third and fifth. Okay, fifth semiconductor as a substitutional impurity. If this group second will enter into gallium arsenide as a substitutional impurity, and it will replace, let's say it is replacing this group third element such as gallium arsenide. Okay, such as gallium arsenide. This is what, let's say here this is my zinc. Okay, so this zinc is what? This zinc is second group element. If this zinc will replace this gallium arsenide from here, let us say zinc will come here and it will replace the gallium. Yes, gallium. Now see, zinc has 2. How many outermost shell electron? 2. Only 2. Okay, so now zinc has only 2. So this arsenic has 5. 5 over 2 is how many? 7. Means there is a one deficiency. There is a one electron deficiency. Yes, there is a deficiency of one electron. To complete the octet is equal to what? 8 electron. So it is not stable. So this need what? This need one electron more. Means it will act as what? It will act as a acceptor. So therefore, this group fifth element, if it will replace group third element such as gallium arsenide. Okay, so then it will act as what? It will act as a acceptor. It will act as a acceptor. This group means this zinc will accept as what? Zinc will act as a acceptor impurity. Okay, acceptor impurity. Now if similarly, if you see, let's see, let me remove this first. Okay, so this one. So now I am saying that what we have seen, first we have what? We have entered the second group element such as what? Beryllium, zinc, cadmium. Out of that you can take any element. This is like a zinc is from group second. Okay, so now this group second is entering into what? Entering into the compound semiconductor such as gallium arsenide, and this zinc has replaced what? Gallium arsenide. Okay, so initially if you see here gallium is there, but this zinc has replaced the gallium and it will act as a, and to become an acceptor impurity. Where? In compound semiconductor. Similarly, if this zinc of group second element will replace what? Will replace group fifth element instead of what? Group third element. If it will replace what? This group fifth element. Okay, so this is my zinc. Now this zinc. Okay, so in place of zinc, let's say here we are taking, now first we have what? We have entered the zinc into this. Okay, so into the gallium arsenide. Okay, as a substitutional impurity. Now we are entering what? Group. We are entering group sixth element. Group sixth element such as what? Such as selenium, and tellurium. If you will what? If such as this group fifth element, this is selenium and tellurium. If these group element, okay, if these element if these element will enter into what compound semiconductor, will enter into compound semiconductor. So this is my group sixth element. If this group sixth element, let's say tellurium, group sixth element tellurium will enter into where, into gallium arsenide, into gallium arsenide. If it if this element will enter into this compound semiconductor such as gallium arsenide, okay, so as we know gallium has what, 3 electron in its outermost shell, and arsenide has what, arsenide has five element in its outermost shell, means this compound semiconductor is stable, okay, stable. Now what is happening, this sixth group element such as tellurium is entering into this gallium arsenide compound semiconductor as a substitutional impurity by replacing what, by replacing the group fifth element such as arsenic, okay. So now it is what, it is replacing this group sixth element such as tellurium is replacing the group fifth element such as arsenic. Now see here, gallium there in place of arsenic, now tellurium. So this is my tellurium, okay. So tellurium, and tellurium has what, how many outermost shell of electron, there is a sixth element, okay. These are six element, no, 6 electron. How many electron in the outermost shell of this tellurium is 6, because it belongs to what, group sixth element, and here is a 6 electron in its outermost shell, and gallium has how many, 3. Gallium has how many, 3. So 6 3 is how many, now 9. 6 3 9. So 9 means there is a excess electron, there is an excess electron. One excess electron means it is what, donor, it is what, donor impurity. So it will act as a donor impurity, okay. It will act as a donor impurities, okay. So this is a donor impurity. So donor impurity will occur when group sixth element such as tellurium will enter into the gallium arsenide such as compound semiconductor, and replace the arsenide, replace the group fifth element such as arsenide. Then this will act as what, this tellurium or group sixth element will act as a donor impurity in what, in compound semiconductor. Similarly, if group second element such as zinc will enter into the gallium arsenide compound semiconductor as a substitutional impurity, and replace this group third element such as gallium arsenide. Now here how many total electron is there, 7, but there is a deficiency of 1 electron to become stable, so therefore it will act as an acceptor. Why? Because it need 1 electron more to become stable. But if you see in case of group sixth element, when it will enter into the gallium arsenide as substitutional impurity and replace this arsenide element, and hence here this group of element, this compound semiconductor now has total 9 electron, 1 excess electron. This indicate what? This indicate that this group sixth element tellurium is acting as what? Acting as a donor impurity. Whereas this zinc element which belongs to group second element will act as a acceptor. So that is why it's somewhat complicated situation that we get in case of a compound semiconductor. Then in case of what? In case of elemental semiconductor like silicon and germanium. So now if you see the corresponding ionization energy, okay, if you see corresponding ionization energy, so this is what, this from here what we understood that what we have taken the group third and fifth element. Why? Because if you see group third means what? 3 element, means group third means what? Third means the element which belongs to this group third element. It has what? It has how many electrons in its outermost shell? It has 3 electrons. Similarly, this group fifth has 5 electron in its outermost shell. Means this group third and fifth compound semiconductor itself is a stable. Okay, so it's a stable. Okay, so now if we are just entering the next new element into this compound semiconductor like group second element, that is like zinc. If we enter the zinc into this compound semiconductor, into this lattice. Okay, so if we enter zinc into this lattice as a what, as a substitutional impurity, and if it and replacing this group third element, then that time this zinc will act as what, act as an acceptor impurity. Because why? Because there is a deficiency of electron to become the stable. Okay, so similarly, if from group sixth element such as tellurium, if we will enter this tellurium into this lattice of what, into this lattice of group third and fifth element, means gallium arsenide lattice, if we will enter this tellurium into this gallium arsenide lattice as what, as a substitutional impurity, then this tellurium will replace what, arsenide. Okay, arsenide element which belongs to from group fifth element, and this tellurium has how many electrons in its outermost shell? There is a 6 element, and this gallium arsenide, gallium has 6, gallium has a 3, 6 plus 3 is equal to 9, means there is an excess electron, one excess electron, which is the indication that this tellurium which belongs to group 6 element is what, is act as a donor impurity. So now if we see what, ionization energy, the corresponding ionization energy for this what, for this impurity is smaller than that of the impurity in silicon. So this is what, ionization energy. If you see the ionization energy that is required, ionization energy that is required for this impurity in gallium arsenide is smaller than impurity in silicon semiconductor. Okay, so therefore this ionization energy that is required for this impurity in what, in gallium arsenide is smaller than that of the impurity in silicon semiconductor. What actually we have seen, if we summarize this is what we have, gallium arsenide. This is my gallium arsenide. First you see here, so this is here gallium arsenide compound semiconductor. Gallium arsenide. If you see, gallium has 3 electrons in its outermost shell, and arsenic has 5 electrons in its outermost shell, and it is stable. Okay, so it is stable. Now if you see group, so if I will enter what, group second element like zinc. If I will enter this zinc, group second element, this zinc which has only two outermost shell electron. Okay, if this zinc will replace this gallium arsenide from here. Okay, so this is gallium arsenide. Now if this zinc will replace this gallium arsenide from here, so this is my zinc. Now this is zinc. Okay, this is Zn zinc. Okay, so it has only 2 electron, and this is my arsenic. It has 5 electron. 5 2 is equal to what, 7. So total outermost shell electron is how many? 7. But 7 means there is a deficiency of 1 electron deficiency. Okay, so 1 electron is less, so it is acting as a what, acceptor. Okay, acceptor. So there is what, deficiency there is a deficiency of one electron. Okay, so deficiency of one electron indicate what? Accepted impurity. Okay, accepted impurity for zinc. Similarly, if I will add what? Group sixth element such as tellurium has how many outermost shell electron? Six. Okay, so these are six. If I will enter this tellurium into what? Into gallium arsenide. If I will enter this into gallium arsenide, okay, gallium arsenide compound semiconductor. So here I am replacing this arsenide. Okay, if we will replace this arsenide, then what we will get here? This is my gallium arsenide. Gallium is as it is. So this is what? 3 outermost shell electron, and this arsenic is replaced by tellurium. Okay, so tellurium has how many outermost shell electron? 5. 6. Okay, 6 plus 3 is equal to what? 9. 9 means it has excess electron. Excess electron. One excess electron indicate what? Indicate that this tellurium is what? Donor impurity. What? Donor impurity. Okay, so this is my donor impurity. So this is acting as a donor impurity. So now it is clear now. Okay, so it is clear. If we add second group element, okay, so it will indicate what? Accepted impurity. If we will add group sixth element into gallium arsenide, and it will replace arsenic element, and it will indicate what? And there is a, then after that there is a total number of electron in its outermost shell is 9. 9 means one excess, means it is indicating donor impurity. Okay, and corresponding ionization energy for this impurity in gallium arsenide is smaller than that of what? Than that of impurity in the silicon semiconductor. Okay, so now see here. Similarly, the ionization energy of what? Donor impurity. Ionization energy of donor impurity is smaller than that of what? Ionization energy of accepted impurity. Why? Because of what? Effective mass of electron is smaller than that of what? Smaller than that of hole. Okay, so if you see here similarly, so ionization energy of donor impurity. Ionization energy of donor impurity is what? Is less than what? Less than ionization energy of accepted impurity. Okay, so this is what? Ionization energy of donor impurity is less than that of ionization energy of accepted impurity. Why it is? It is because of what? Because of effective mass. What? Effective mass. Because of effective mass of what? Effective mass of electron. Because of effective mass of electron is what? Electron is smaller. Effective mass of electron is smaller than what? Then hole. Effective mass of hole. So this is because of that. Okay, so now we have completed about, we know also about ionization energy. What is this ionization energy? What actually is this? So ionization energy is nothing but it is the minimum amount of energy. Ionization energy is nothing but it is the minimum amount of energy that is required to elevate what? To elevate the electron to the conduction band. From where? From the outermost shell of an atom. Okay, or you can say that the minimum amount of energy that is required to detach what? to detach the electron from the outermost shell of an atom into the what? Into the conduction band. Conduction band in the sense means free space. Free space within the semiconductor. That is nothing but interatomic space. What? Interatomic space. How much energy is required to detach the electron from the outermost shell of an atom, okay, so that this electron will become free and it will move through the interatomic space within the crystal, semiconductor crystal. Okay, so this is what nothing but ionization energy. Okay, so that ionization energy is required for the donor and acceptor impurities that is present in the gallium arsenide is smaller than that of the impurity that is present in the elemental semiconductors such as silicon and germanium. Okay, so that is, now see, we are going to see also group, what, group fourth element. Group fourth element, if we will enter what, if we will enter the group fourth element into the lattice of what, into the lattice of group third and fifth element, which is nothing but gallium arsenide, then we will see what is the indications of about the silicon, means how it is behaving. Is it acceptor or donor impurity? Okay, so now see, from group this is my group fourth element. Okay, group fourth element like group fourth element like silicon. Okay, so now if a group fourth element like silicon enter silicon enter the what, enter the lattice of what, lattice of compound semiconductor compound semiconductor. Okay, so now we are saying that if this group fourth element such as silicon enter the lattice of compound semiconductor, that is nothing but gallium arsenide. Okay, what we are saying now, if group fifth element, this silicon will enter into the lattice of compound semiconductors such as gallium arsenide as what, as a substitutional impurity, as a substitutional impurity. Okay, substitutional impurity. Okay, so now if this compound, if it will enter as a substitutional impurity, and that time this silicon will act as what, this silicon will act as what, act as donor impurity impurities. Okay, it will act as a donor impurity. Now see, what actually I want to say, that let's see here. So this is my what, this is my gallium arsenide, this is my gallium, and this is my arsenide, First what we did, first case what we did, in the first case we entered what, we entered the group second and group sixth element as a substitutional impurity into what, into the gallium arsenide. Okay, so now we are entering what, we are entering the group fourth element. Okay, we are entering the group fourth element into the lattice of compound semiconductors such as gallium arsenide. So now gallium arsenide, now we will see here how it is acting. Okay, so is this silicon as impurity, means which type of impurity, like donor or acceptor? See here, this is silicon. How many outermost shell of electron this silicon has? 4. How many? 4. So this is my silicon, and it has 4 outermost shell electron. Yes, now this gallium arsenide has how many? 3. Arsenide has how many? 5. Which one I will replace? Which one? So let's say we are going to replace what? This is my fourth element. Okay, if I will replace what? If I will replace gallium arsenide. Okay, so let us replace this gallium arsenide first. If I will replace gallium arsenide here, okay, if I will replace gallium arsenide by the silicon, by entering the silicon as substitutional impurity, then here silicon will come. Okay, so silicon has how many outermost shell electron? 4. And this arsenic has how many? How many? 5. 5. 5 plus 4 is nothing but what? 9. 9 means what? One excess electron. What? One excess. One excess electron is there. Yes. One excess electron indication is what? Indication is nothing but donor. What? Donor impurity. Donor impurity. Impurities. Donor impurities. Means what? Means this silicon, when this silicon is entered as substitutional impurity into the compound semiconductor as gallium arsenide, and if it will replace this gallium arsenide, then it will act as what? Then it will act as donor impurity. Donor impurity. If this silicon atom replace this gallium arsenide. Okay, if the silicon replace this gallium arsenide, then that time it will act as a donor impurity. How we know? We know that this has how many electron? 4. Arsenide has how many? 5. 5 plus 4 is equal to 9. 9 means what? 1 is excess electron. Excess electron indication is what? That silicon is nothing but it's a donor impurity. Donor impurity. That is the indication of excess electron. Excess electron. Why? Because we want to detach this excess electron. Okay, excess electron. Then that time it will act as a donor impurity. Donor impurity. Now, next case what? Next is here. Next now we are going to what? Now we are going to replace arsenide instead of gallium arsenide. We are going to replace arsenide. Now see arsenide. This is what? Silicon. So this is gallium arsenide. Gallium is as it is. Okay. So this is my gallium, which is as it is. It will not change at all. Okay. So it has how many electrons? 3 electrons. So now this will replace this arsenide. So in place of arsenide, silicon will come here. Silicon. Now see here. Silicon has how many electrons? 4. Gallium has how many electrons? 3. 4, 3 is what? 7. 7 means what? 7 means there is a deficiency of what? There is a deficiency of 1 electron. There is a deficiency of 1 electron. Deficiency of 1 electron. Since this deficiency of 1 electron indication is what? It indicate what? It indicate acceptor impurity. What? Acceptor impurity. It indicate acceptor impurity. Yes, acceptor impurity. From here, what conclusion we can make? Conclusion is that if this silicon replace gallium arsenide, then it will act as a donor impurity. Donor impurity. If this silicon replace arsenide, then that time it will act as a acceptor impurity. Acceptor impurity. Similarly for germanium. If germanium replace gallium arsenide, then it will become donor. If germanium replace what? Arsenide, then it will become acceptor impurity. Acceptor impurity. So this is about what? Group 4th element such as silicon and germanium. Okay, when we will enter these into what? Into this group 3rd and 5th element. 3rd and 5th element means what? Means compound semiconductor. Then we will see the different results. Okay, so that we are seeing what? It is what? Complicated situation of what? Of this compound semiconductor as compared to the elemental semiconductor. Now if you see here, it has been what? It has been experimentally found that the germanium is an acceptor impurity and silicon is an what? Is a donor impurity. It has been experimentally found. Okay, experimentally found. So this germanium is what? Germanium is an acceptor. Germanium is an acceptor impurity. Germanium is an acceptor impurities, and silicon is a donor impurity. Silicon is a donor impurity. That is what when we enter these element, these element into the lattice of what? Into the lattice of gallium arsenide. Into the lattice of gallium arsenide, then that time germanium will act as a acceptor impurity and silicon act as a donor impurity. Germanium act as a acceptor impurity means germanium will replace what? Will replace group fifth element such as what? Arsenide. Okay, and silicon will replace group third element such as gallium. Okay, such as gallium. So therefore, it has been experimentally found. Okay, so germanium acceptor impurity and silicon donor impurity. So this is all about what? This is all about group fourth, group third and fifth element. Group third and fifth semiconductor is nothing but it is a compound semiconductor. What? Compound semiconductor. Compound semiconductor, or you can say this what? Compound semiconductor means it's a hybrid semiconductor. It's a hybrid. You can say also hybrid. It's a hybrid means combination of two element. Hybrid. Okay, hybrid mixture of two element. Okay, so it is making what? One semiconductor. So that's why this is what? Direct band gap semiconductor material. It's a direct band gap semiconductor material. What we have seen here, we have just seen that if we will add different group element into this what? Into this lattice of gallium arsenide, we are getting different result in term of what? Impurity. In term of impurity. Okay, so these are all about group third and fifth semiconductor, which are nothing but compound semiconductor or hybrid, or you can say hybrid semiconductor. Okay, so that's all for today's lecture. That is about group third and fifth element. To group third and fifth element semiconductor. Okay, so which means compound semiconductor or hybrid semiconductor. Okay, here we have entered the element from different group and we have got the result in term of impurities. Okay, either donor impurity or acceptor impurities. Okay, so that's all for today's lecture. Thank you very much. Okay.